Hi, welcome to the second lecture of Triple 107. In this part of the lecture, second part of lecture 7, we'll be talking about we're still going to be talking about frequency modulation and phase modulation, but we will be looking at the spectral characteristics of frequency modulation. And since frequency modulation and phase modulation are related to each other, we will only be studying one. Of course, when you have a signal, introduced to you a signal, we'll always be talking about the bandwidth, the power, how do we solve them, how do we characterize them. And this is the part of the lecture where we talk about that. So in the previous meeting, I introduced to you two forms of angle modulation, phase and frequency. They're related to each other. It has four properties. Okay, and okay, let's move on. How do we analyze the spectrum of an FM or a PM wave? Recall that for FM, you have an instantaneous frequency given here for some arbitrary message signal with bandwidth W. So if you want to save frequency content, maybe we should just reduce or set KF to small value so we can reduce the bandwidth and we still retain the same properties. That's not how it works. So yeah, the instantaneous frequency is not the spectral frequency. So even your FM wave would just shift in frequency, the total frequency content of the signal is not taken from the instantaneous frequency. That's why it's instantaneous frequency, right? So if you want to analyze the spectral content of FM or PM waves, then we have to perform a Fourier analysis. Okay? And there's also a trade-off between bandwidth and SNR. Okay, so if you have a small KF, then you have a small bandwidth. That's actually intuitive, but it still that's not how it works, but it's still intuitive, okay? But because you have a small sensitivity in frequency, you'll have a harder time to extract and demodulate your FM wave. Okay? And we want KF to be large enough such that we are able to detect the FM wave using a frequency demodulator, okay? Or an FM demodulator. Okay? So there's a trade-off between them. Right, so just some preliminaries. For this meeting, we'll only be analyzing the frequency content of FM waves. And the theories of that can be applied to PM waves later on. We want to study the spectral properties of FM waves for a single tone message signal and extend the analysis for any arbitrary M of t. So why a single tone message signal only? Well, recall that any message signal can be expressed as a sum of single tone sinusoids, right? So if without loss of generality, we can actually analyze the single tone properties of FM and then extend that using this relationship between a message signal and its frequency content. And we'll first analyze the narrowband FM wave and generalize that to a wideband FM wave. Okay. So consider a tone modulated FM wave. The instantaneous frequency using this, we have a message amplitude A sub m. The instantaneous frequency is equal to this. Okay, where your F, just a note that your message frequency, as always, is much less than the carrier frequency. So delta F here is the maximum frequency deviation, and that is equal to the frequency sensitivity multiplied to the amplitude of your cosine wave, of your message wave. So the instantaneous angle can now be expressed as this, and beta here is called the modulation index of your FM wave. Where beta is, since you're going to integrate this after, if you want to get the instantaneous angle, you integrate the instantaneous frequency, and you get your instantaneous phase. So if you integrate your cosine, you'll get sine divided by 2 pi fm. Okay? And you get this value for beta. So it was taken from there. So recall that phi of t is equal to 2 pi integral of m of tau d tau from negative infinity to some time t. Okay? And with that, you can solve for beta. Okay? So this is the modulation index of your FM wave. So now the actual FM wave can now be expressed as this. Okay? And if we use the sum of angles identity, so you have a cosine A plus B can be expressed as cosine A, cosine B, minus sine A, sine B. Okay? So that's what happened here. And for narrowband FM, your modulation index is much, much less than 1. What happens if you do that? Your cosine, very small, will just be equal to approximately to 1. The sine of something very small is approximately the angle. So with that, your narrowband FM, see here, can now be expressed as this, or if we factor out the, if we expand this, we can look at it in, we can, what do you call this? The formula again for cosine okay, and you get you transform this equation into this equation, so that's why you have this expression right here. Okay, and we compare that with your AM wave expression. Your AM wave expression looks like this. Your FM wave expression looks like this, approximately, at the very least. But there's a difference in the signs. Okay, and your FM and AM modulation indices depends on FM and AC respectively. So it seems like a narrowband FM signal has the same properties as a full AM wave. So this is a full AM wave. Okay, so your AM wave and narrowband FM wave would essentially have the same transmission bandwidth to FM. However, there are differences in their phasor diagrams. So as you can see here, your message signal is in phase with the carrier signal for AM, but for narrowband FM, your FM signal, your message signal is out of phase by 90 degrees. So that would mean that the carrier power and the message power would be approximately equal. Compared to your AM phasor diagram, well, the carrier power is larger than the message power. Right? So the implication of that is that the resultant phasor for AM is always in phase, while for narrowband FM, you have the same magnitude for your message phasor and your carrier phasor, but they're not in phase with each other. Right? Now let's look at the wideband case of your frequency modulated signal. So recall that we have this expression earlier. We can transform that to its baseband equivalent, complex baseband equivalent for an easier analysis. So in complex exponential form, we extract the complex carrier from this expression and get the complex baseband equivalent, which is equal to this function right here. So this is the complex envelope of your FM wave. And the spectral characteristics of this can be used to analyze your wideband FM. So recall that if we have a bandpass signal, so let me just redraw that. Oh wait. Recall that if we have a bandpass signal, so with a spectrum that looks like this, Let's say FC is right here. Its complex baseband equivalent will just translate the positive component into the baseband spectrum. Okay, so it will look like this, but the amplitude is bigger. Okay, so we're taking advantage of that fact and try to analyze the complex baseband of FM, and knowing the spectrum of a complex baseband of FM, we are able to get the spectrum of the actual FM signal. Okay, so the complex envelope is this. The signal is periodic with the frequency f sub m. So you can check that out for yourself. But since it's periodic, we can use the Fourier series representation to analyze the frequency content of your FM wave. So how do we solve for the Fourier series coefficient? If you want to get C sub n, then we integrate complex baseband equivalent with, okay, from one period. There you go. But how? Can we even apply Fourier analysis here? Let's try. Okay. We use what we call the Bessel functions to solve for the Fourier series of your FM wave. So let's try to integrate your expression here, e to the j 2 pi, sorry, yeah, e to the j beta rather. Let me just correct that. Or let's just write it here. Okay, so try to integrate this expression right here. So is there an answer? It's actually difficult to solve this. Luckily, somebody did it for us already. And the solution there is the Bessel function. The Bessel function is the solution to this integral right here, which is similar to what we got earlier. And this is graduate level stuff. So if this is the Fourier series coefficient, then if we try to integrate that using this form, then we can just define C sub n here to be equal to AC times Jn of beta, where Jn of beta is a Bessel function of the first kind. Okay. So it's an nth order Bessel function of the first kind, and we can now express our complex sinusoid, or sorry, our complex baseband equivalent of the FM wave to be equal to this. The coefficients of your different frequencies of your frequency contents of your signal is the Bessel function, and your actual bandpass FM signal is equal to this. Okay, so the FM wave expression can now be written in this expression right here. And to get the discrete spectrum, we just apply the Fourier transform of this signal right here, and you will see that the height of the different impulse functions will be defined by the Bessel function. Okay, so what is the Bessel function? So the Bessel function, to get C sub n based on the modulation index and of course the value n, we can use the Bessel plots or the Bessel table to get the different values of the Bessel function. For example, if we want to get a third harmonic third harmonic component that is n is equal to 3, given a modulation index equal to 3 and the amplitude of the carrier equal to 1, then we just get j sub 3 of 3, and the other side j sub negative 3 of 3, and we get these values for the coefficients of your third harmonic. Okay, some properties. For different integer values of n, we have this. So the negative side of your Bessel function, if you have negative n, they're equal if n is even, and it will be negative if n is odd. Okay? And for small values of the modulation index, if beta is very small, you will see that at n is equal to 0, which represents the carrier, the j naught of beta here is equal to 1, and j1 of beta here is equal to, well, beta over 2. Okay? And the others would be approximately 0. And this actually predicts what we got earlier when we were looking at narrowband FM signal. So this wideband FM analysis is the generalization of course, all FM signals. And now if we add all the coefficients of the Bessel function for varying values of n at a given value of beta, it will always be equal to 1. And this, because of this property, the FM signal has a constant transmit power. Right? Recall that to get the power of a signal, you need to get the area of its frequency spectrum squared, magnitude spectrum squared. And if we do that, since the Bessel function defines the coefficients of each impulse function of the frequency components of your FM signal, you add all that square, and then you add all that, it will be equal to 1. It shows us that it proves that it proves the property of FM signals that you have a constant transmit power that is defined by the carrier amplitude. Okay? And that's the end of this part of the lecture. So if you have any questions, do not hesitate to leave a comment in the comment section below. Thank you for listening. See you next meeting.